Hi, everyone. Thanks so much for joining. We're just going to wait another few seconds to let people fill into the webinar, and then we'll get started. Apologies, I was just muted. It looks like some people are still joining, but let's get started. All right. So thank you all so much for being here and joining us for this webinar, New Energy Conversations with Early Career Energy Researchers. My name is Megan, and I'm the Manager of Academic Initiatives at the Irving Institute for Energy and Society at Dartmouth. And I am very excited to welcome everyone here today. So this speaker series is part of our New Energy Initiative, which aims to empower and raise the profile of early stage researchers in energy and climate. And part of this effort is highlighting scholars here on this webinar. And we also host an annual in-person New Energy Summer Summit that helps early career energy and climate researchers increase their capacity for interdisciplinary scholarship and collaboration. So I'm very excited to introduce today's moderator and bring our speaker out in just a minute. But first, just a quick note. The first half of the program will be a presentation from our speaker, and then we will have an opportunity for discussion. So please feel free to enter your questions for our speaker using the Q&A icon at the bottom of your Zoom screen. And you can do that at any time during the program, and then we'll get to as many as possible after the presentation. So to kick us off, I am thrilled to introduce our moderator for the session. Dr. Erin Mayfield is the Hodgson Family Assistant Professor of Engineering at the Thayer School here at Dartmouth, where she leads the Sustainable Transitions Lab. And the aim of Dr. Mayfield's research is to develop computational decision support tools to address real-world problems and facilitate multi-stakeholder decision-making processes. She's participated in several large-scale collaborations on infrastructure transitions, including the Net Zero America Project, the REPEAT Project, and the Fifth National Climate Assessment. During the Biden-Harris administration, Erin served as a strategic advisor in the Office of Policy at the U.S. Department of Energy, and she was the Assistant Director for Net Zero Pathways in the White House. And prior to academia, Erin was a practitioner working with and in vulnerable communities on hazardous waste remediation, environmental litigation, and infrastructure planning. She's held positions at the U.S. Environmental Protection Agency, U.S. Congress, Princeton University, and the Environmental Law Institute. So I am very excited to welcome you here, Erin. Thank you so much for being here. And I'm going to pass it over to you to introduce our speaker.
Thanks, Megan. So it's my pleasure to introduce Dr. Wilson Ricks. Wilson is a postdoctoral researcher in the Zero Carbon Energy Systems Research and Optimization Lab, or the Zero Lab, at Princeton University. So I first met Wilson about 5 years ago when he was a first-year PhD student in the Zero Lab, and I was a postdoc. So I'm really excited for him to be here today. So Wilson's research uses optimization-based energy systems modeling tools to explore the impact of technologies and policies on the decarbonization of the energy sector. His primary areas of focus include next-generation geothermal power and temporally granular emissions accounting. And with that, I'll turn it over to Wilson.
Thanks, Erin. And thanks to the Irving Institute for inviting me to speak. I'm going to share my slides now and get right into it. So bear with me. All right. So today is focused on next generation geothermal power and the role it could play in the energy system. This is largely going to effectively be a summary of my dissertation research on this subject. And specifically today, when I talk about geothermal, I'm going to be talking about its role in the electricity sector, though it may have use cases elsewhere. And the kind of larger context for this, of course, is that we need huge amounts of carbon-free electricity. If we're serious about decarbonizing by, say, 2050, That means we're effectively going to need to add roughly 2 times all current total generation in just new clean generation by that date, if we want to hit that goal. And a kind of key challenge here is that, well, we have a large suite of commercialized, cost-effective clean energy generation technologies and increasingly battery storage. These are not necessarily sufficient to finish the job, to truly eliminate fossil fuels from the electricity sector cost effectively. Um, and that's because while wind, solar, and batteries are certainly going to be necessary and will certainly play an extremely large role, there's a pretty extensive literature at this point demonstrating that you need something else to, really fully decarbonize electricity 24/7. You need something else to at least play a role in the system. That's something being either long duration energy storage that can help you cost effectively displace fossil power during, say, long periods of wind and solar droughts, the fabled Dunkelflaute, of winter weeks without wind and low sun, when you need huge amounts of batteries otherwise, or clean firm power, which is effectively clean generation that is not weather dependent. And for this reason, it can actually be the case that even if you have clean, firm resources, like geothermal power, that are more expensive on a per megawatt hour basis than wind or solar, it can still be cost effective to include them as part of your net zero system, because they're more valuable than those other resources in the effectively the times when it matters, when wind and solar would really struggle to deliver. Now, when we look at the pool of resources that could feasibly fill this clean, firm niche of clean power not dependent on the weather, it's actually a pretty small roster, and a lot of them have various trade-offs or limitations. In this list I have up here, I've kind of organized them in order of lowest to highest resource potential. So biopower, which is of course questionably zero carbon, depending on exactly how you do it, also has extremely low resource potential because we need to eat food too, and there's constraints on land use for things like biodiversity, and a lot of competition for biomass in other net zero sectors like aviation fuel, for example. Hydropower, similarly clean, firm, though somewhat weather dependent, based on rainfall, and also fairly geographically constrained to regions with large elevation changes, for example. And in the US, we've pretty much used all of the large hydropower we're ever going to build. Fossil with CCS, again, questionably zero carbon, could possibly get close. Moderately higher resource potential, still dependent on fossil fuel reserves and injection basins. So you couldn't do this everywhere, but you could do it a lot of places. And then nuclear power, fairly few limitations in terms of total resource potential, though maybe some non-proliferation issues. But today I want to talk about the kind of fifth major technology category in the clean firm niche, and that's geothermal power, which today doesn't really factor into the conversation very much because conventional geothermal power falls at the very bottom end of this spectrum. It is clean, it is firm, and it's available hardly anywhere. It's basically a rounding error in total electricity generation today, which is why I want to focus more directly on next generation geothermal, which has the potential to unlock much, much higher resource potential and by extension play a much larger role. Now, geothermal power overall is really an extremely simple concept. It basically just recognizes that the Earth is hotter on the inside than it is on the outside. And you can use this geothermal gradient to drive a heat engine to do useful work like generate power. The advantages of this are it has lower zero emissions because you're not burning a fuel. It's firm, so it's available around the clock because the Earth's heat doesn't depend on the weather. And it has extremely low surface land use because all you really need on the surface is a turbine. Now, when you want to generate geothermal power today, or in the last 100 years, what you typically use are natural hydrothermal features. So you'd find an area where three particular properties coexist, these being heat, so obviously the energy source in the equation, water or some other fluid to act as the energy carrier to transport that heat from underground to the surface, and critically permeability, so effectively a reservoir underground where water can flow freely and sweep heat from the subsurface, and allow it to be extracted efficiently, because otherwise you basically have no way to access the large heat reserves in the body of rock. And when you do find all these three features kind of coexisting, the technological approach is very simple. You just drill a well into your natural reservoir, you pump water out of that reservoir, use it to generate power, and then inject the cooled water back underground to refill the reservoir. We've done this for over 100 years at this point. The first geothermal plant was built in Italy in 1904. But despite that long history, geothermal in a conventional sense makes up a just minuscule portion of total electricity generation. It's about 0.5% globally, 5% in California, an example of a place with fairly good resource potential, but also very high electricity demand. And there are some select places in the world where it's a much larger proportion, like Iceland or Kenya, where it makes up about 50% of total power generation. But the upshot of all this is that I think it'd be fairly uncontroversial to say that conventional geothermal can't play a major role in a global energy transition because the resource is just so limited. These natural hydrothermal reservoirs are just extremely rare geologic features, and they don't even always exist in the places where we actually need power. But heat itself is not rare. And that's a key point here, is that if you drill down deep enough under, for example, the United States and very likely many other areas of the world, you can get to temperatures high enough to generate cost-effective geothermal electricity, so greater than 150 Celsius, without having to go extremely deep. Now, there's variations in exactly how quickly you get to those temperatures, but in general, heat is much more common than heat combined with permeability and fluid in the form of these natural reservoirs. And this brings me to enhanced geothermal power, which is the next generation technology I want to discuss today. It's been getting a lot of, I think, a lot more attention in the news since I started working on it 5 years ago. But this is designed to answer the question of what you do when you've got hot rock underground, but you don't have a natural geothermal reservoir. And the answer here, at least the approach in enhanced geothermal, is that you build one yourself using hydraulic fracturing to create the flow paths to effectively engineer your own reservoir. So this is basically drilling your injection and production wells and creating a fracture network between them. This is obviously a very stylized illustration, but you create a fracture network, a series of fractures along these wells that allows water to flow from the injection well through the fracture where it picks up heat because of the large surface area of the fracture, into the production well and up to the surface to generate power. And enhanced geothermal, or EGS, which is the acronym I'm going to use from now on, is well understood to have a terawatt scale resource potential in just the US, likely multiple terawatts, potentially tens of terawatts, in just the first few kilometers of the subsurface. So very high potential, and it's been recognized for a while, and the technology has been researched off and on for decades, even going back to the 1970s at the Fenton Hill project in Los Alamos. But it's only recently that it's actually really seemed like it's been getting off the ground and being really seriously pursued, largely because of both increased demand for clean power and because the shale oil and gas boom over the last couple decades actually brought to scale a lot of the same techniques that would be necessary to do cost-effective enhanced geothermal power. So directional drilling and hydraulic fracturing, which is maybe a underappreciated positive externality of that revolution. And so this brings me to a few kind of major research questions that spurred a lot of my dissertation, um, which I'm going to be kind of discussing in the rest of the presentation today. The first of these questions, which is maybe the logic of doing in this order, kind of makes more sense when you think about how much work you have to do to answer each one of these. But the first question I chose to look at in the context of my PhD research was, when you have this new technology, this new enhanced geothermal power plant, let's say you're building one for the first time or the 10th time, what exactly are the capabilities of this technology compared to both conventional geothermal power and other technologies that supply electricity today? And if you're building one of these plants, how can you optimize its design and operation to make it as valuable of a zero carbon electricity resource as possible? Um, Beyond this, we wanted to answer the question of, okay, let's assume that you've figured out how to, make this the best thing it can be. What kind of role could it play in the energy system? Where does EGS fit into the niche of clean firm power? And just how does it interact with things like wind, solar, batteries? Where does it benefit? Where does it compete? And finally, in a kind of broader sense, let's say you're a policymaker concerned with whether we should invest in commercialization of EGS or a developer, we'd like to have a sense for how big of an impact this technology could actually make at different geologic scales. So maybe in regions where there's higher resource potential or lower resource potential, how big of a deal is this to the decarbonization project overall? I'm going to start at kind of the most constrained level, the plant level, and answer the simplest of these questions, which is, how do you make EGS valuable? And the background here is that conventional geothermal power plants are a pretty simple technology operationally. They are baseload power almost universally, which means they generate their maximum rated potential at all times. Um, the logic behind this, it makes sense. It's that when your fuel is just water from underground, you're not paying anything for it really. And so it hardly ever makes sense to actually generate less than your maximum potential because you're not paying anything to generate. But the value of baseload power in decarbonized energy systems is a bit unclear, because as we increase the use of variable renewable energy, wind and solar power, we see that the net demand for power is also becoming increasingly variable. So this is basically total demand minus wind and solar. And this is giving us things like the California duck curve, where if you're a baseload resource during the middle of the day in California, let's say you're generating a constant amount, your power is now worthless for, from basically 9 a.m. to 6 p.m., which wouldn't have been the case before. And it means that you've effectively paid the same amount up front for your, big expensive geothermal power plant. And now you have to make back all of that investment in just nighttime hours. And it also means that you can't really take advantage of the spikes in value of power, say, during the evening ramp, where you're generating just as much as you would have before. And so basically resources aren't very well equipped to fill these gaps. And the theory may struggle to play a very cost-effective role in a decarbonized grid. But while conventional geothermal power is a baseload resource, the kind of key realization here is that enhanced geothermal power doesn't necessarily have to be. And in fact, this concept of flexible operation of enhanced geothermal power, which in this paper we called in-reservoir energy storage, is something that's been investigated all the way back to the 1990s during some of the earliest EGS test projects. And the principle here is that unlike conventional geothermal reservoirs, which are kind of these large permeable things that are connected to surrounding geologic systems and are not necessarily confined, so water flows into them and out of them. EGS reservoirs, because you create them in rock that is not permeable, that is not necessarily dry, but does not hold like an aquifer, they can actually retain fluid and pressure much better than a conventional reservoir. And what this means is that if you were to, say, take your EGS power plant, you're injecting water at a constant rate, you're producing it at a constant rate, suddenly you reduce the flow out of your production well, so you're still injecting water into that reservoir. The water is then trapped in the reservoir, more or less, and the pressure in the reservoir rises as the fractures themselves expand, as the water slightly compresses. And you can do this when power demand is low and you don't actually need to produce any power to increase the pressure and accumulate fluid in your reservoir. And then when you get to a point where the value of power is very high, you can open up your production well, and that excess pressure can drive that excess fluid out in a concentrated burst where you get more power than you would have otherwise. This is effectively a form of energy storage. And the hypothesis here was that this could be a kind of key value add for enhanced geothermal power compared to conventional technology. And so the approach we took in this particular project was just to investigate what are the actual capabilities of EGS power plants operating in this way. How long can they store power? How efficiently? How kind of strange are the actual behaviors and how controllable are they? And then when you optimize the operations of a plant around this, how valuable does it actually become if you assume that you can exploit differences in electricity prices? And the approach we used here was first to actually simulate the operation of flexible geothermal reservoirs using fairly sophisticated numerical reservoir simulations, and then to build a linear optimization model of a flexible geothermal power plant that could optimize the sizing of the different components of the plant and the actual dispatch of the plant to take advantage of these capabilities. And I'm not going to get into the nitty-gritty details, but we were basically successful in building an optimization model that almost perfectly replicated the behaviors that we saw in the much more complicated reservoir simulations. So these plots are basically showing us doing different storage cycles in both the simulation and the optimization model and getting almost identical results. And what we then did with this model was we optimized the operations and sizing of different components of these plants against various input electricity price series. So we assumed we had a plant in, say, Southern California. We put in the prices, hourly electricity prices over a year, and we said, okay, how much value can you get out of this kind of cycling behavior compared to just flat baseload operations? And what we found was that the answer is a lot. You can actually get a lot of excess value by operating flexibly compared to just base load. Though this depends on the market, depends on how variable electricity prices are. We found an improvement in value of more than 50% in Southern California, where right now you have high amounts of curtailment due to grid bottlenecks and lots of solar power. And the plants were very eager to kind of undertake these complex operations to really exploit those periods of very high electricity prices that they could get by kind of storing power during some times and shifting it to other times. And this would often entail the oversizing of the surface turbine to actually allow you to get more power out of those periods of higher burst flow. So it had some implications for how you should actually approach the design of enhanced geothermal power plants. We also found that we performed some kind of controlled tests on just the capabilities of these plants. We found that the effective energy storage capacity of one of these simulated reservoirs was on the order of days to weeks. So this is extremely long duration energy storage by comparison to something like a lithium-ion battery. And we found that if you compare the relative total generation of a plant that's doing one of these cycles to one that just generated baseload, you get an effective round trip storage efficiency of 60 and 90%, which is surprisingly high for a long duration storage technology. Something like hydrogen storage is on the order of 30 to 40%. So this is a potentially key advantage. The kind of difference between this and other long duration storage technologies being that you have to build a whole geothermal power plant to access this. So it really only makes sense if enhanced geothermal itself makes economic sense. I want to move on now. This kind of project was basically us confirming that this flexible operational mode was something that had potentially high value, and differentiated EGS compared to other conventional approaches, and something like nuclear power, for example. And I want to move on to work that we did trying to assess how EGS could integrate with the broader electricity system and the role it might play and the impact it might have. This work was still kind of predicated on the question of what can operational flexibility do for us in this case. And it was focused on looking at how flexible EGS, or flexibility for EGS could change the long run value and deployment potential and overall role of enhanced geothermal power in low carbon electricity systems. And this was a kind of much more expansive piece of research. It involved not just reservoir simulations, but also the incorporation of enhanced geothermal power into a broader electricity system capacity expansion model, where we focused on the role it could play in the Western US grid in a hypothetical decarbonized year 2045. And because we needed the model to be able to choose whether to build EGS or not, we needed to have a good sense of what the relative resource quality was across the Western US. So we did a pretty detailed resource costing exercise to build supply curves, basically showing how much at a given kind of like technological advancement assumption, how much of this resource could you build in each region at a given cost. And at the end of the day, we were assessing things like EGS deployment, impacts on electricity sector costs, across a range of scenarios, particularly focusing on the question of flexible versus inflexible. This was, again, integrating the kind of more focused or technology-specific plant-level model that we built in the previous work, with a broader optimization of the bulk electricity system in our model GenX. And so we had the sizing of all these various components of each individual power plant or EGS power plant in the grid, as well as the operation of those components that then fed into the broader electricity demand balance constraints of the system model. And we used an 11-zone representation of the Western US for this study. And we also, so this slide is just showing a model of our simulated reservoir design. So this is what on the left, a more sophisticated enhanced geothermal reservoir design might look like. You'd have several wells drilled from the surface, probably from the same well pad, and then deviated horizontally. This is showing 3 production wells in orange and 2 injection wells in blue, and you basically inject water into these wells. The water flows through the fracture network that's created off of each of these wells, from the injection wells to the production wells and then back to the surface. And we use temperature and depth projections to basically cost out the geothermal EGS resource in each of these resource areas. When we look at what the model actually does when you offer EGS as a deployable resource, both inflexible and flexible, we find that flexible geothermal power really complements renewables quite well. So specifically wind and solar power, and in fact, specifically solar power. The reason for this being that when you have a baseload resource, so the plot on the left is showing EGS at the very bottom in the dark red. And this is inflexible operation. The fluctuations you see are actually from surface ambient air temperature. It affects the efficiency of the power plant. But you see that basically it's generating constantly, even during the middle of the day when you otherwise would have lots of solar power available. And it also is generating a kind of a flat amount. So during periods when the grid is really strained, say this part on the left, you need more of the pink and brown resources, which is gas with carbon capture and some sort of low carbon fuel combustion. Um, Versus on the right graph, when you have flexible EGS, you can see that it actually starts getting out of the way during the middle of the days and shifting generation to nighttime. So this is the same number of wells drilled in each case. But on the right, you can see that it's actually contributing more value by generating a huge amount during the night times when solar isn't available, allowing cheap solar to fill in during the days, and reducing the amount of that, in particular, that brown gas with CCS resource now doesn't actually appear in this plot at all because the system didn't need to build any because EGS can fill that same load following role. Another key result of this work was that we identified multiple paths to market impact for EGS. So what I'm showing here is a baseline case where we assume current drilling costs for enhanced geothermal power, a more sophisticated reservoir design than has been currently demonstrated, but no advances in drilling cost, and baseload operation. And when we allow the model to decide whether to build EGS in this case, we get about 15 gigawatts of total installed capacity in the Western US, which is way more than we have geothermal power today, but still a pretty tiny portion of total generation. And the actual reduction in electricity system cost compared to a case where we don't allow it to build EGS is only about 0.5%. So this isn't making a huge impact on the overall cost of a decarbonized grid. But if we allow EGS to operate flexibly, this is the exact same resource, but only like same costs, everything, but only allowed to operate flexibly. We see that deployment more than quadruples in an optimal case. It now makes up almost a fifth of total generation in the region, and it reduces the cost of the system by up to 8% at this point. So really starting to make a significant impact on electricity costs. Now, alternatively, if we kept it baseload, but just reduced the cost of GGS significantly, we can also get to pretty high deployment. So if we can just make it cheap, then baseload is fine still. And it makes up 2/5 of generation and reduces costs by 14%. But the real holy grail we found was if you can do both, if you can both make EGS cheaper and allow it to operate flexibly, then you get over 100 gigawatts of deployments. This is larger than the current existing US nuclear fleet. And it's now reducing the costs of zero carbon electricity supply in the Western US by almost a quarter, which is just an enormous impact. Now, that's obviously one hypothetical future. But this is assuming a decarbonized year 2045 where you have EGS available at scale at reasonable cost. And so one question we were really keen to answer, which the next bit of work really tries to tackle, is how might we actually get to this future, particularly from where we are now. And the background here is that since we started this work, there's actually been some pretty substantial advances in EGS development in the field. There have been, when I started working on this was basically just theoretical. But starting in 2023, we've had multiple multi-megawatt field tests of enhanced geothermal systems. So a 3-megawatt pilot project by a company called Fervo Energy in Nevada, which has started operating in 2023. A DOE-funded test site called Utah Forge also did a successful flow test in 2024. And then Fervo again built a 10-megawatt flow test in last August 2024, and they say they're on their way to a 100-megawatt demonstration project coming online by next year. These flow tests indicated that you can get good connection between these wells via these artificial fracture networks. And also, actually, one of them showed that you can operate flexibly because we got an RBE grant to demonstrate flexible operation in the field based on some of this previous work. And it turns out that it basically works as we would expect it to in the simulations. Now, there are some remaining uncertainties. We don't know how these systems are going to perform over the long run in terms of whether they keep their heat well. We don't know how much water they're going to lose over the long run, which is a pretty important factor. And we need to understand how reservoir behavior evolves, especially in response to flexible operation. But overall, there have been some very positive developments. And so now the question really becomes, these prior studies have assumed that EGS is available at competitive cost and commercial scale in some future date. But in reality, as a nascent technology, it's going to face scale-up constraints. It's likely going to see its costs start higher because it's new and come down over time via what we call learning by doing, which is the same phenomenon that led to solar and wind and battery costs declining massively as they hit greater and greater deployment. And so some open questions here are, where might early EGS actually come in terms of its cost? And where might it first be market competitive? And how could the scale and timing of those initial deployments affect its overall long-run deployment potential? And so in this study, we kind of structured it in two components. The first was attempting to establish a near-term cost baseline for EGS. So using the latest field data from some of these early projects, which we didn't have before, to actually create empirically grounded national scale EGS supply curves for the near term. And the second part of this project was to then use these supply curves as the inputs to a multi-stage electricity system capacity expansion modeling exercise, where we included learning by doing as an endogenous property of the model for EGS and a few other emerging technologies. And this was basically to look at how the actual deployment of EGS could evolve over time if we assume that it follows a similar, benefits from learning curves similarly to wind and solar power and comes in at costs similar to the ones that we are projecting in the early 2030s. So if we look first at the results of this costing exercise, these were again constructed based on a cost model we developed previously and published data, assuming some fairly incremental advances in system design, and based on national temperature depth maps for the geothermal resource quality. This plot shows costs. Our baseline is the actual baseline cost projection, and then the high and low cost values are just plus 50% minus 33% to the cost of the subsurface. But what we find is that generally outside of the Western interconnection, so outside of the Western US in Texas in the east, near-term baseline EGS costs are likely too high to be commercially competitive. So this is $100+ a megawatt hour, roughly, unsubsidized. I think this is unsubsidized. Whereas in the Western US, they could actually be reasonably lower, especially at what we're calling near field sites, which are places close to conventional hydrothermal systems or natural hydrothermal reservoirs. The areas around those are well known, and they're areas where there's basically unusually high temperatures close to the surface. And so they're kind of prime prospects for early EGS deployment. And we find that it could actually be fairly competitive in those areas. This is again just a visualization of where EGS is more or less cost effective. You can see in general, hotter and shallower resources are going to be cheaper. So at 2.5 kilometers depth, it's really only near these labeled hydrothermal sites where you can see significant potential around them. Whereas if you go much deeper, suddenly larger and larger expanses of subsurface are at the temperatures necessary. Though the Western US is still going to be generally more cost effective than the Eastern US. Now, when we put these supply curves into our system model, we find that EGS actually does have quite high potential in the long run under supportive climate policy, that being a key caveat in this day and age. And so these plots are basically showing at the top section, each column is a policy case. So we've got current policy, which includes the Inflation Reduction Act. I have a case without the Inflation Reduction Act in the appendix. and a net zero policy where we assume that there's actually a net zero goal at the end of all this in the 2050s. And the first row here is total installed EGS capacity. The second one is EGS cost divided into both the well fields, so the reservoir part and the surface power plant. And then finally, total electricity cost for consumers. But we basically find that if you can get early deployments at the best sites, so which happens most of the time in cases at our baseline EGS costs, then this virtuous cycle of increasing deployment and reducing cost from learning leads to potentially hundreds of gigawatts of EGS nationally. So very similar in scale to something like wind or solar. Whereas a lack of early deployment, for example, in this red line here, could really stunt long-term potential because it slows down this virtuous cycle. And also that if we can successfully scale things up, then we reduce the cost of decarbonization nationally very significantly compared to this gray line here, which is cases where you don't have EGS available. And notably, what we found is that in the cases where you do unlock this learning curve potential, adoption is not limited to the Western US where the resources are highest quality. And in fact, we see a very large amount. We actually see more EGS east of the Mississippi than west of it in a lot of cases, which is kind of funny. This is largely because the electricity demand in that part of the country is so much higher. But it's impressive given that this is largely seen as a very niche regional resource in this day and age. And in general, learning-based cost reductions make differences in resource quality less important. If it's, say, 50% cheaper to build a well field in the Western US than the Eastern US, that's a much bigger difference if it's 50% of $100 a megawatt hour versus 50% of 50. Now we also wanted to look at whether these results were obviously plausible, because we can't just say, oh, the model says it's gonna be too cheap to meter. So we looked at drilling cost reductions as one potential approach to reducing the cost of EGS overall. We found that these could contribute because drilling in hot, hard rock is still less mature than standard oil and gas drilling, which has been done, in millions of wells. But drilling overall is mature enough that this is unlikely to bring down costs massively, at least enough to deliver the kind of national scale adoption we see here. Instead, what we find is that most of the cost reductions that we need to see happen could plausibly come from improvements in reservoir design. So like I showed you that reservoir before with the 5 well laterals, you could add more well laterals in parallel, basically incrementally increasing the amount of subsurface area accessed by each well. You could also add them on top and on bottom. You can make the lateral section longer, so you drill the vertical only once, and then you access 10,000 feet of lateral instead of 5,000 feet. And basically, all of these advances, if you kind of add them up, could plausibly lead to a very large reduction in the overall cost of EGS well field, and unlock these very promising long-term pathways, though obviously real-world validation is needed. So the overall conclusions I want to leave you with today are, first, based on the currently demonstrated performance and reasonable learning rate assumptions, there is a very plausible case to be made that EGS could become a major source of carbon-free electricity generation if it can achieve large-scale deployment within the next decade. So that early deployment is really a key, make or break moment. The second part is that if EGS can benefit from learning-based cost reductions, we found that it could actually likely meet the entire clean firm power needs of the continental United States, if needed, so on its own. So there is a world where if we don't see successful scale up of other clean firm options, EGS could potentially fill that role on a national scale, which is a pretty, this is a very novel result. I think it's largely previously been considered something that's only relevant to the Western US, but it is not necessarily. So with that, I think I'm gonna wrap things up and open up to questions.
Thanks, Wilson. So to remind participants, there is a question and answer function. So please kind of submit your questions there. So I will start out with a question. One, kind of thank you for going through this. It's wonderful to see how your research has evolved since 5 years ago. So my first question is, what are some of the real or kind of perceived barriers to deploying enhanced geothermal at scale? So beyond kind of some of the technological constraints or barriers.
Yeah, that's a great question, and there are definitely barriers. One of them is just grid interconnection, which is a barrier to everything. But EGS is definitely not immune because, especially right now, these projects are generally going to occur at the sites where the resource quality is the best. And so you're going to need, you're not immune from, you can't just build this in your backyard and avoid transmission. This needs to get grid interconnection rights just like any other resource, and that can be, lead to uncertainty and long waiting times, which can be really crippling for an emerging technology where you've got, high interest rates and a real need to get a successful demonstration under your belt. Other barriers, water use could be one, depending on that. I mentioned that as one uncertainty here. There's some amount of water that's lost at the subsurface when you operate one of these facilities. And so you will need a source of makeup water, the size of which is kind of dependent on how much water you're losing, which is reasonably constrained at this point, but not fully. So that's if it's very large, then that could become a major constraint. I'll note that these systems don't necessarily need to use fresh water, so that's a major benefit. They can use saline water or wastewater. In fact, the Geysers geothermal installation in Northern California actually does inject wastewater from Sonoma County. But that's a potential constraint, especially in the Western US. And seismicity is one thing that is being, I think, like a real laser focus of the geothermal industry right now. Because just like hydraulic fracturing for oil and gas, there's risk that if you do this in the wrong place and you do it too recklessly and without kind of the proper precautions, that you could cause earthquakes through the hydraulic fracturing. This is something that has not happened yet at any of the test sites, and there's been very successful monitoring. It's also much reduced risk compared to oil and gas fracturing because you don't have to take water out of the wells after you fracture it and then re-inject it somewhere else underground to dispose of it. And that's actually where most of the seismicity from oil and gas comes from, is the re-injection of wastewater. But this is something where there have been seismic events associated with EGS tests in the past when they've done like right on top of fault lines. And it's something that is absolutely critical to avoid.
So we have a question from the audience from Honor Passau. So the question is, I believe you did not mention the cost of the surface power plant. How sensitive are your estimates to reductions in the cost of the surface power plant?
Yes, I didn't mention the cost of surface power plant because it is a more mature technology, and so there was kind of less novel work to be done on estimating those costs. But I can go back to can I go back? Yeah. To this slide where in the middle plot you can see the dotted lines represent the cost reductions in the surface plant. They're generally lower than the subsurface, and that's because we're assuming that binary cycle power plants, which are what EGS plants use, are more mature. There's about 4 gigawatts of total deployment of binary cycle power plants in the world today. And they cost anywhere between, I would say, $2,000 and $4,000 a kilowatt. So they're not cheap. And actually, when you get to reasonable cost for the subsurface, the surface power plant becomes potentially half or even the majority of the total cost of the installation. So if we can make these cheaper, that would also be really key. There's actually a lot of signs that you probably could make them reasonably cheaper, especially with mass standardization, because current geothermal power projects are incredibly boutique. They're basically you build a custom 10 megawatt power plant for a custom project that's trying to exploit this one unique reservoir that can only support that much. And it's got like its own resource temperature, chemistry, etc. And so there have been some studies showing that if you can actually standardize the production of these turbines and, produce like 10, 50 megawatt units at a time, that you can drastically reduce their cost. So this might be something where we can see significant reductions. Still, obviously, need to be proven out in the field. We didn't, unfortunately, go too deep into sensitivity around surface plant costs here, but in general, cheaper is better, and we have a pretty good sense of where they are right now.
So suppose you are a hypothetical institution in northern New England, and you're a risk-averse institution that has a net zero goal, and you're trying to consider pre-investment decisions in geothermal, both in terms of meeting kind of a large thermal and kind of electrical load. Would you recommend investing in enhanced geothermal in that setting? In the like 3 to 5 years, you have
Yeah,
to make a pre-investment decision.
I think, well, there is actually an institution that is doing this. Cornell is actually working on their own. It's unclear whether it's going to be true enhanced geothermal, but they've drilled a very deep hole on their campus, and they're, I think, exploring the option to use that for heat supply, which is something that I didn't cover at all. Geothermal is probably much more cost effective for heat than it is for power because the efficiency of these power plants is so low because it's probably like less than 20%. So you get 5 times as much heat. Now it depends on the heat needs of campus, and also depends on how risk averse the the campus is. I think if you wanted to be super safe, you would probably wait until there was like 100 gigawatts of this stuff, and the deployments were kind of creeping east from the areas in the Western U.S. where there's much higher resource quality. But it's something that I think should be seriously considered. Um, a major uncertainty for any individual decision maker is just like, what are the temperatures 5 kilometers under my site? Which we can have a reasonably constrained estimate of, but still pretty high uncertainty unless you actually drill that test well or someone near you has drilled a test well. So that's something where being a first mover could be a bit of a risk. Depends on your appetite. But in theory, you go deep enough, you should find something.
So I have kind of a policy question.
Yeah.
So you had kind of your different policy scenarios, kind of the one bounding is kind of your net zero scenario. What types of policies do you see kind of bridging the gap between current policies, and I say that with hesitation, and kind of a net zero policy? What are the kind of the actual policy instruments to move between current policy and net zero policy to support geothermal?
Yeah. So I guess there's a question of like what I use in the paper, what I assume in the paper, and what is what I would recommend. In the paper, our net zero cases were basically assuming that Inflation Reduction Act tax credits continue, and that I believe starting in 2035, there's a national clean electricity standard. So I think it goes from 80% 2035 to 90% 2040, 95% 2045, and 100% 2050. Either 100% net zero, or we had one where it was basically you can miss that if you pay a carbon price of $300 a ton. So there's one of our cases where gas can basically stay in the system, just paying a very high carbon price. That's not necessarily me commentating on what I think is the best approach to net zero, but it's just a kind of some illustrative examples. We did spend some time in the paper looking at potential near-term policies that could boost EGS deployment. And there were a few that are obviously boosting near-term deployment could be a key tool in unlocking long-term potential. one thing I think can be really cost effective, or can be really cost effective from a societal perspective, is uh, at least for any emerging technology, is some sort of deployment mandate. So if you have, you know, paying for, say, 5 gigawatts of deployment of EGS or advanced nuclear or anything else at a national scale is really not going to make a have a big impact on budgets, but could have huge long-term dividends if it helps something get down the learning curve. Um, there's also just increases in subsidies, which may or may not be enough to put something over the edge, and demand for round-the-clock clean power. This kind of gets into my other research on 24/7 carbon-free electricity. But if you are a corporation and you're no longer concerned with just saying I bought as much solar power as I consume power and therefore I'm net zero, and you want to actually say I'm powered by clean power around the clock, then that creates kind of implicit demand for something like geothermal, which can help you cost effectively do that. So those are all things that could really help performance, or help kind of spur initial deployment. Um, I will note that one of the biggest catalysts so far, in my opinion, has actually been California's requirement for, I think, 1 gigawatt of geothermal deployment by 2030 or 2032, and then another 1 gigawatt in the first half of the 2030s. And this has actually been responsible for one of the largest power purchase agreements, which was signed by Southern California Edison and Fervo Energy for, I think, 300 megawatts of enhanced geothermal. So that's an example of policy being like an incredibly, and just a state level policy, mind you, um, being a really key driver of early adoption. Especially when, again, this is an unproven technology at this stage, at a large commercial scale. Like, any individual buyer is probably going to be very risk averse unless they're encouraged somehow.
So we're near time, but I'll ask one last question. And so without maybe revealing what you're kind of working on now, if you don't want to, but I'm curious, where do you see kind of this modeling going? What are the next kind of big questions?
Yeah, I think one really big question is, we've done this in theory, but how does it work in practice in terms of like actually designing uh, real EGS systems that can operate flexibly and act, and the whole ecosystem around that actually takes that theoretical value and translates it into real world value. So that's things like contracts, that's things like system planning. We There's, the state of California is probably going to have to start considering enhanced geothermal power as a resource sooner rather than later, if it really starts to get going. And so whether or not system planning exercises can actually capture some of the unique and complex capabilities of these plants is, I think, going to play an important role in basically how they factor into those resource plans. And this is something where the modeling will have to evolve, because the models I built here for these academic studies are extremely complex and basically they completely blow up the runtime of the system model, and they're basically impractical to use for actual planning. So kind of the maturation of the methods we use to represent EGS is, I think, one area that I'm particularly interested in.
Thank you. So it looks like we're at time, so I'll pass it back over to Megan to wrap up.
Great. Thank you so much, Erin. And thank you so much, Wilson. That was a really great talk. It was wonderful to get a deeper dive into your research, and we will definitely be following what you're doing next. So thank you so much for being here. And thank you again to Erin for moderating a great discussion.
Thank you for
So
inviting me.
yeah, thank you. So we have, this is our final talk of this academic year, but we'll be back in the fall. We have some more talks coming up during the next academic year. We have Julius Flesch from the Norwegian University of Science and Technology. He'll be talking about his work in technological innovation systems and sustainability transitions. And we have Gage Hills from Harvard. in electrical engineering who is developing future generations of energy efficient and environmentally sustainable computing systems. So stay tuned for that when we're back in the fall. And thank you again so much to Wilson Ricks for being here and joining us from Princeton, and for Erin Mayfield for moderating. And we hope to see you again. Thank you.